is blind to definitions. So we've defined plus 3 someplace to be plus partially applied to 3. But the unification mechanism doesn't take that into account. So if we try to do rewrite here, that will fail. What we need to do instead is to unfold plus 3, to replace the defined atom by its right-hand side. And now unification works fine. And we can do the rewrite, and then the proof is finished. Okay, so you'll need, and now that's back. Okay, so you'll often need that. Why wouldn't it, by the way, just unfold definitions before doing the rewrite? Why would that be a bad idea? What happens if they're recursive is one thing. Exactly. So if we unrolled all of the definitions before doing the rewrite, we would, because we haven't done the rewrite yet, we'd have to unroll all the definitions, every definition of everything. And that would result in a gigantic term. Now we would maybe successfully rewrite one little bit of it, and then what would be left would be this hideous gigantic thing. So there's a method to this madness. So there's a reason not to be a little smarter in a lot of cases. The same thing happens with the simple tactic. It doesn't unfold as much as you sometimes think it ought to. And the reason is that the way it's defined is a delicate balance between the convenience of simplifying things when they're kind of obviously simplifiable and avoiding the inconvenience of unfolding too much and blowing up the goal state that you're looking at. Okay, inversion is an extremely important tactic. We'll use it a lot. And it's a little bit more difficult to understand than the ones that we've seen, but not too much. So inversion is used on, for the moment, equality hypotheses. In general, you can use it in other situations, but let's look at the special case for equality. So if we have an equality hypothesis, we have something in the context that says some expression equals some other expression, and each of those expressions begins with a concrete constructor, then what do we know? Well, if those constructors are different, then what do we know? So if I have a hypothesis that says, for example, 0 equals successor of x, what do we know? We know that we've introduced an inconsistency someplace, and that hypothesis is nonsensical. So if we've got an inconsistent context, then we should be able to prove anything, and indeed we can. And saying inversion to that hypothesis will prove any goal. Okay, now, what about the case where C and D are the same? Then what do we know? So we've got C applied to some list of arguments and D applied to some list of arguments. And C again applied to some list of arguments. So then what do we know? So first of all, the lengths of the argument list must be the same because it's the same constructor and a constructor has a fixed arity. And then each of the pairs of arguments, one on this side and one on this side, must be pairwise equal. If those arguments themselves are explicitly constructed things, then we can keep going. So for example, successor of 0, if we have a hypothesis that says successor of 0 equals successor of 0, then once again it's nonsensical and we should be able to prove anything. And inversion will get that in one step. So what inversion does is it takes an equality hypothesis and it kind of squeezes all of the juice out of it that it can get by observing that different constructors can never be equal, that's nonsensical, and the same constructor leads to a whole bunch of sub-equality facts. So, in the interest of time, I'm not going to show you the example of this, but you'll see that that when you use inversion, what will happen is a bunch of equalities will get added to your. All right, let's do one. All right, so easier just to show you than to say it. So we want to show n equals m, and what we have is successor of n equals successor of m. So we can do inversion on EQ, and notice what happens. So we get a new hypothesis that was generated by the inversion from the arguments to successor. So that gets stuck in the context, and it gets used to rewrite the goal. So this proof is actually finished. Okay, that is not the file I want. Still learning to use this full screen mode of Chrome, which is not actually helping me very much. No. No. All right. Okay. Where were we? Okay, so that was inversion. All right. One last thing for this file. When we're doing inductive proofs, we have to be careful about the form of the induction hypothesis. And here is a typical example. It is actually worth looking at this, even though that's going to screw up Chrome again. All right. So suppose we're trying to prove that that if n equals m, in the sense that if we're trying to prove that the test does n equal m returns true implies that n is really equal to m. Right, this is kind of a correctness property for the BEQ NAT definition that we gave. We would obviously want to prove it by induction, because n and m are inductive things. We're probably not going to make much progress without induction. Okay, so we do intros, we do induction. We got the zero case, which is easy. Let's skip over it. Now we got the successor case. And now if you look at the induction hypothesis, you might already be a little bit worried. Because, what does it say? So we've got some fixed number m, and we're trying to show that the successor of n prime is equal to m, knowing that n prime is equal to m. This can't be right. Okay, so I mean, it's true that if from this we could show this, then we would have established the original thing. But we're just not going to succeed from that induction hypothesis. We're not going to succeed in showing this. So what went wrong? The intros was wrong. Why? Right. So we, at the beginning of the proof, notice, we intros not only n, the thing we were doing induction on, but also m, which fixed m, right? Doing intros effectively says pick an m. So we said pick an m and now do induction on n. So we're trying to do this inductive proof for varying n, but always for the same m. And that's just wrong. We can't prove it that way. The induction hypothesis is insufficiently general. So the induction hypothesis that we want is this that we have here, but with a quantifier at the front that says for all m. Right, so we need a more general induction hypothesis. How do we get the more general induction hypothesis? Exactly. We do a little less intros at the beginning. So here is the better version. So if we just do intros n, and then the induction, and then let's skip over that. Okay, now we have a better induction hypothesis, the one that we want. We need to now do the intros, right? So we have to do a little bit of work in each case that before we were trying to do once and for all at the beginning. But that's life. This is the correct way to get through the proof. So we do the intros here, and then we can finish the proof. And I won't bother going through the details. It's the same reasoning that we've seen a bunch of times for inductive proofs about numbers. So the point of this example was just to show you that it's easy to get the induction hypothesis a little bit wrong. And this is something that even people that are fairly careful about their hand proofs often trip over, because hand proofs are generally not careful about exactly the order of quantifiers versus induction. All right, so you tend to just say, you have some quantified fact that you're proving, you just say by induction on whatever it is, by induction on n. And then when you get to the point in the proof where you're using the induction hypothesis, you kind of implicitly rely on the fact that you can do it for a general m. So you may be surprised. I am often surprised when I'm doing this kind of proofs. Oh yeah, I got the induction hypothesis a little bit wrong with regard to quantifiers. And it's just because as informal mathematicians, we're just not used to doing it. Okay, so when you find yourself in a funny state and you can't make progress, have a look at your induction hypothesis and see if it actually does imply the thing that you're trying to prove from it. And often it won't. And the reason it won't is because it's insufficiently quantified. And you need to back up and intros less. Okay, so this will often come up. In a minute, okay, so we can just intros less, right? I want somebody to say no. So what's the problem with that fix? Well, right, if it happened, so I got lucky here. I got lucky because I had written the for all n before the for all m, so I could choose to just do the intros on the n and not the m, and everything was fine. But if it had happened that I had written the theorem with the quantifiers in the other order, then I'd be stuck. And for that, there's a tactic called generalized dependent, which I think we'll actually see in the next chapter. Yes, we will. But I'll just tell you about it now because we're almost at the next chapter anyway. So in those situations, your friend is generalized dependent. So what that allows you to do is basically intros a bunch of things and then unintros a few of them. Right, so generalized dependent is the opposite of intros. You point it at a particular identifier or a collection of identifiers, and it regeneralizes them. And the dependent part is if you generalize something whose type depends on something else, it will also drag that automatically into the regeneralization process. So it regeneralizes the thing that you point to and whatever other things it needs to in order for that to make sense. Is it better than choosing the order of quantifiers carefully? Yeah. Our goal should always be for the statement of the property to be as clear and natural as possible. So we haven't quite gotten to the point where the proofs that we're doing are right only. Right? You could, with a little practice, learn to look at the proofs of the size and complexity that we're dealing with and kind of figure out what's going on. But we will quickly pass that stage and enter the stage where basically Coq proofs are not readable without an IDE in front of you to show you what state the proof script has gotten us into. Just like all imperative programming, right? You can't understand what it's doing because there's all this hidden state that's being manipulated by the by the program. So these are imperative programs in the worst sense. In fact, it gets even worse because you get to the point where when you start using proof automation, you can't even understand it with an IDE, and the proofs become entirely write-only. And that's just a fact about the way that people do business with proof assistants. So Coq doesn't have a very good kind of declarative proof style. Isabelle is much better in that regard. But Coq, the benefit that Coq gets from that deficiency is the scripting facilities are extremely powerful, and you can use them to write programs that build proofs in completely amazing ways. So there's a delicate balance between declarativeness and programmability in this world that I think people are still working to understand, honestly. Okay. So that's that about varying the induction hypothesis. Here's a useful little thing. Almost all of the tactics in Coq have variants that, instead of working on the goal, work on some hypothesis. So, for example, simple. Instead of saying simple, you can say simple in H, or indeed you can say simple in star, and it will just simplify everything in sight. Usually you don't want to do that. You want to aim it at a particular hypothesis and simplify that. So almost all of the tactics that you'll see have a bare version that works on the conclusion and an in version that works on a hypothesis that you say. A particularly interesting one of those is apply in. So apply in takes a theorem and one of the hypotheses and applies the theorem to the hypothesis. So in a sense, it says comment about that on the screen. This is forward chaining style of proof. So normally in Coq we begin with the theorem and we try to whack on it and break it down into simpler and simpler sub-goals until finally they're all gone. So that's kind of backwards chaining. That starts with what we want to show and works backwards to what we need to show it. And that is the most natural style in Coq. That's the one that Coq supports in the most kind of native way. But it's often convenient for us as humans to think in a forward chaining style. So to begin with the hypotheses and think, well, how can we, what can we do with that, and so on. And apply in is the way to do that. So apply in takes a hypothesis and turns it into something that we can derive from it using a previously established theorem. Okay. Another useful point about tactics, we've seen the destruct tactic. We've always so far used destruct on variables. But actually, you don't have to use it only on variables. You can use it on arbitrary compound expressions. So for example, let's not take the time to do this one in the IDE, but here's a silly theorem that we're trying to prove. We define a function that does some computation with numbers, and then we want to show that it never returns true. And we can do that by destructing larger expressions. If you work through the proof, you'll see the points at which this is helpful. So destruct takes an expression and says, is the value of this expression, well, so if the expression returns a Boolean, as these do, it says, is the value of that whole expression true or false? So it gives you two sub-goals. Okay, so having told you that you can do this, I'm now going to advise you not to do it. And the reason is that often the expression that you're destructing is also something that you need to reason about. Okay, so in this particular silly example, we can take this expression BEQNAT N3 and replace it everywhere by true in one subgoal and by false in the other subgoal, and we can finish the reasoning that we need to do. Typically, that's not the case. Typically, what we'll need is to know that BEQNAT N3 is equal to true without actually throwing away that expression. And the way that we achieve that is by a tactic called remember. Okay, so let's do that here. Okay, so here's a different silly function at the top of the screen. And now we want to show that only odd numbers, only for odd numbers does that thing return true. So a typical property that you might need in your day-to-day life. And the way we do it is we do intros first. And now if at this point, let me show you the bad version where we do the wrong thing. So if we had just done destruct of BEQNAT N3, notice what's going to happen. We're going to get two subgoals. In each of them, that whole expression, BEQNAT N3, replaced by either true or false. And now here, we're supposed to show that if something silly, then N is odd. All right, so we just can't do that. So what happened was we replaced too much, or we threw away the thing that we were analyzing. What we want is to have a case analysis that says, well, suppose that BEQNAT N3 is equal to true, and then prove the result. And then in the other case, suppose that it's equal to false, and prove the result. So we get that by using remember. So the first thing we do is this remember, and remember takes an expression and a fresh variable name and clips out that expression and puts it in the hypotheses as equal to the variable name that we gave. So what we've done is we've made up a variable E3, and the remember has given us the hypothesis that it's equal to BEQNAT N3. And now when we do destruct on E3, we're going to replace E3 by true in one branch and false in the other branch, leaving the BEQNAT N3 alone. And this hypothesis is going to turn into exactly the equality assumption that we need, either that compound expression equals true or it equals false. Okay, so if we do the destruct, now we have, okay, we still have the silly one that we can't use, EQ, but we also have the useful one, HEQ E3, that we can get some juice out of to show that N is odd. Any questions? Yes, yeah, so we don't always have to be making progress on the main goal. There's a tactic called assert that introduces a sub-goal of which is whatever you want. And when you finish proving it, it puts it in the hypotheses to be used for whatever else. No, you don't need a QED. QED is only for the very end where you're switching back into the top level.
They give you the sub-goals.
Assert is probably related to that.
I think lets you continue along the same goal and then you prove the asserted goal afterwards.
The sub-goal ordering is different.
Okay, good. So general comment. Coq has many, many tactics, lots of which do almost the same thing. And any particular Coq user tends to a particular set of tactics that they're used to using, and then, you know, for any proof that they write, there would be another proof that another user would do in a somewhat different way. And it all works out because, like I said, the tactic proofs are kind of right only anyway. And what matters is the lemmas, the sequence of lemmas that you go through to get to the final conclusion. And those are written in a smaller subset of the language. I prefer to break things out as lemmas because I find local asserts to be just a little bit clunky, that they kind of get in the way of the flow of the main proof. But as with any proof, it's a matter of taste. So if the little fact that you need at a particular point is of no interest whatsoever at the top level, then just stating and proving it locally is fine. No, they would probably not give exactly the same proof term. The assert would probably turn into an application of an anonymous lambda, whereas the use of a named lemma would turn into an application of that name. So almost the same, but not quite. Okay, so a complete story about that would get us into deep waters. In ordinary lambda calculus, when we write down on the board, let x be this lambda term, and now we write down another lambda term that uses x. This is kind of a meta definition, and what we mean by the second lambda term is the one where we've meta substituted the definition of x for its uses. In Coq, it's more complicated. So in Coq, these definitions are real. They have a real status in the type theory. And there's a notion of reduction, an actual, you know, arrow with a particular subscript, particular flavor of reduction that replaces definitions by their right-hand sides. And that, for example, is the kind of reduction that simple doesn't always do. Other questions? Okay. All right. Occasionally, apply doesn't have enough information to do its thing. If we just say, apply this theorem to the goal, it will fail. Because unification doesn't instantiate all of the variables in the conclusion of the theorem that's being applied. Okay, so how can that happen? So, for example, with transitivity. Shall I just show you this? Yes. Okay, so here's a little lemma at the top of the screen that says equality is transitive. Okay, proving that is no problem. But now, suppose we want to use that lemma to prove this fact. All right, so we want to prove that if that first list is equal to the second one and the second one is equal to the third one, so this is just an instance of the transitivity of equality. So we should just be able to use apply to get it. So can we? No. Why? So if you look back at the definition of trans EQ, so what we were trying to do. We had some goal that we were trying to prove. Apply is going to unify that goal with the conclusion of trans EQ, which is n equals O. Okay, so it's going to succeed in doing that unification. That's going to give us a particular value for n and a particular value for O. What were those values? They were AB and EF. Okay, so it instantiates n to AB and O to EF. And now it has to generate subgoals for the two hypotheses, n equal m and m equal O. Those subgoals use a variable m whose value we don't know. Okay, so the process of unifying the goal with the conclusion of this theorem instantiated two of the metavariables, two of the variables m and O, but it left instantiated n and O and left m uninstantiated. And so we don't know what the subgoals should be. So that's why the apply failed. And what we can do to help it is we can say apply trans EQ with, and we can give it the value for m. Okay, so this is just giving a little helping hand to the unifier that says, well, you didn't find out from unifying what the value of m was, so here it is. Okay, and now we can finish the proof. Okay, so let's review where we are. So we've seen a bunch of tactics now, so this long list. And we'll see a few more in the next couple of chapters, but basically this is almost a working set for doing quite a bit of interesting proving of facts about little functional programs. And, well, there it is. Let's quickly go through the next file because it's short. In fact, I think we actually kind of have gone through it because this is the one about generalized dependent. Yeah, in fact, I'm going to skip this file. So the next file in the normal list is called gen, and it's basically it's got 3 or 4 kind of extended examples, but its whole purpose is to drive home the point that you sometimes have to be careful about having a general enough induction hypothesis, and that you can use generalized dependent to do that if you need to regeneralize some variables. Okay, that's really all you need to know from this file. Okay. So now, in the last few minutes before lunch, let's start with the last file that I'll show you. We probably won't finish this file, but let's get a little ways into it today. And this is where the Software Foundations stream starts to meet the rest of the lectures that we've seen, especially the ones involving dependent types. Because here is where we start to look at inductively defined propositions as opposed to inductively defined data types, and proof objects. So kind of concrete computational evidence. Okay. So I have a property in mind, a property of numbers. I'm going to call my property beauty, just because I like it. And my property is defined in the following way. So the number 0 is beautiful, 3 is beautiful, 5 is beautiful, and the sum of two beautiful numbers is beautiful. So that can be written out in various ways. It can be written out kind of in English. It can be written out in inference rule format. And at the bottom of the screen, we have Cox's way of saying it. So this is an inductive definition of a thing called beautiful. This thing is a proposition. not quite a proposition. It's a proposition indexed by natural numbers. So it's a family of propositions, one for each number. And I think in the text it takes a little while to get to saying this, but it won't surprise any of you to hear that the intention is that some of these propositions be inhabited by terms that are proof objects. These are the provable ones, or the true ones. And some of them will not be inhabited. So for each n, I'm defining here a proposition beautiful of n. And then that proposition may or may not have proof objects that inhabit it. And now, which are the ones that do have inhabiting proof objects? Well, that's what the rest of the definition says. Okay, so the first line says beautiful is a family of propositions indexed by natural numbers and defined inductively. And the rest says B0 is a constructor, that is, it's primitive evidence, you can think of it as an axiom, that 0 is beautiful. So it's an atomic, primitive, unanalyzable inhabitant of the type, of the proposition beautiful 0. B3 is a primitive, unanalyzable inhabitant of the type beautiful 3. B5 is inhabitant of beautiful 5. B-sum is the most interesting one. Its type is, for all m, beautiful n, arrow beautiful m, arrow beautiful n plus m. So what does that mean? It means that it's a constructor, so it's a kind of built-in function-like thing. It isn't a function in the sense that it doesn't have any computation associated with it, right? Just like data type constructors in functional languages have functional types because they take arguments, but they don't compute, they just kind of take their arguments and sit there. So in a similar way,